All right, welcome everyone to another video on induction machines. And in the previous video, we've been talking about the basic operation. So let's actually take a look at that in a little bit more formal manner, trying to understand the concept. Okay. So in the operation, we said the relative motion of the rotor with respect to the stator field is key, right? So we apply three-phase voltages to the stator windings, and that three-phase voltages will result in a three-phase set of currents in the stator. Okay, and that three-phase current will result in a rotating MMF. We talked about this in a previous video. Okay, and that speed of the stator field, we call the synchronous speed, is determined by the number of poles as well as the electrical frequency. Okay, number of poles and the electrical frequency, and this is the relationship to find the synchronous speed. Okay, and this rotating MMF, we said, is going to induce voltages in the rotor. Remember, we have a wound rotor, or we have a aluminum bars that are shorted at the ends. Okay, so remember, if from the drawing from last time, it's going to have bars like that, and then you'll have some form of material, and you'll have the end rings connecting all the bars, so they're shorted. Okay. They conduct current. Okay, so they make loops on the rotor, and it looks like a squirrel cage. Typically, they are not straight like this. They have a skew to improve performance of the machines. We can talk about that later. But there's a voltage induced, and this induced voltage is based on the flux, the cross product between the flux vector by the stator, and this is the velocity with respect to the stator, the rotor of the velocity of the rotor with respect to stator. That's what results in the induced voltage, right? So of course we know that if we have a voltage induced in the rotor, it's going to result in a flux in the rotor, right? And the cross product between them gives us a torque. It'll result in a torque, right? And that torque will accelerate the motor. Okay, that will accelerate the motor. Now, we talked about what will happen at the synchronous speed. Let's say the motor accelerates and gets to the synchronous speed. Okay, when it's at the synchronous speed, what will happen? At the synchronous speed, now there is no relative motion between the stator field and the rotor, right? They're moving at the same speed. Therefore, if you go to our equation here, this velocity, the relative speed, is going to be 0, and you're going to lose your induced voltage. Okay, you're going to lose your induced voltage, and in turn, the torque will drop. But typically, what will happen is, since there are some losses, the friction, all that, it will operate close to the synchronous speed, but it will never reach synchronous speed. Okay, especially when you have some load. All right. Now, one thing that we want to understand before we proceed, right? Okay, we said then there's going to be a field on the rotor, right? We're going to have a field on the rotor, and we have a field on the stator, right? If you look closely in the induction machine, the stator field is operating at the synchronous speed, or the electrical frequency, and the rotor field is based on the speed difference. Okay, so if you the rotor magnetic field will be rotating at the speed that is the difference between the rotor and the stator. Okay, so let me try to explain that. I know in terms of operation, once you understand this, this is going to be very helpful. Now, we said we're going to have a stator field. Let's draw it like this. Have a stator field which is rotating at, so we are representing the flux using flux vectors. So this is a north, this is a, so the opposite side is a south. Let's say this is rotating at omega e. Okay, omega e. Now the field that is induced on the rotor due to the stator field is going to, let's say this vector is like this, but what is the speed of this vector? The electrical frequency of this rotor field, is it going to be the same as the stator field? No, because remember we said that the induced rotor field is based on the speed difference between the electrical frequency or the synchronous speed and the rotor speed. Okay, so if our rotor is rotating at omega r, okay, the rotor if the rotor is rotating at omega r, then the rotor field is based on the difference. Therefore, the rotor field will rotate omega e minus omega r, the speed difference. Okay, the rotor field could be faster than omega e, so then we'll have a negative frequency here. Don't worry about that for now. Okay, that's called the generation, which is possible. For now, the electrical, what we're trying to understand here is electrical frequency. The stator field is rotating at this frequency. If you are to look at only the rotor field, you take out the rotor field and you look at it, and that's going to be rotating at the speed difference between the omega e, between the stator field electrical frequency and the rotor speed. Now, someone might wonder, wait, so we said in order for us to generate torque, right, we said we're going to take the cross product omega r s, right, and then this will result in a sine, which is an angle between the two vectors. Okay, so if these two vectors are rotating at two different speeds, then isn't that angle changing every instance? Right, that's a valid question to ask. Then we have to wait. We have to say, wait, let's think about it. If we look at our motor, right, so we have our stator. This is generating the rotor field. Okay, we have our rotor. The rotor is moving at omega r, right? The rotor is moving at omega r. The rotor flux is moving at omega e minus omega r, rotor flux. That is moving at this speed on the rotor itself, right? And then if I'm to draw my stator flux, I'll just draw it like, I'll draw an arrow like this and say, it's moving like that. Okay, omega e. Now we have to keep in mind that the rotor flux is on the rotor. Okay, so if you are looking at the rotor flux from a stationary frame, so if you are looking at it from outside here, right? If you're looking at this, you're going to see that since this rotor field is on the rotor, for the observer, it will look like it's moving at the same electrical frequency. Okay, that is an important point to keep in mind. It's at this frequency on the rotor. So if you are sitting on the rotor, you will see that this rotor field is moving at this frequency because the speed difference is what induces the rotor flux. However, Since it is on the rotor and that speed adds up to this field, therefore it's moving at the same speed as electrical frequency. That means if we want to regulate, if we want to have an optimal torque production, that means we want to align or control our voltages such that we are at 90 degrees from the state of flux, either this way or this way. Okay, so that all comes down to field-oriented control theory that we've been talking about with regards to synchronous machines, which can be applied here. Okay, so the key points here that I want to highlight is rotor's flux is going to be at omega E, the electrical frequency. The rotor flux is going to be rotating at the speed difference between the rotor and the stator flux, which is omega E minus omega R. However, since the rotor flux is on the rotor with respect to the stator, the stationary frame, or an external observer that is stationary, both the stator flux and the rotor flux will be rotating at omega E, which helps us perform or achieve field-oriented control. Okay, so that's a very important concept, and that's what I wanted to explain, right? How we can generate constant torque if there's speed difference. But we mentioned that with respect to the stationary frame, for the two fields, there is no speed difference because the rotor flux is on the rotor moving with it. Okay, all right. So with that, actually, we are now trying to go into the concept of something called a slip speed. A slip speed, very important concept associated with induction machines. That is basically the speed difference between the synchronous speed and the motor speed. Okay, so if you are on the rotor, this is the speed that you're going to see the flux rotating at. So this is called the slip frequency or the slip speed. Okay, and then there is a way to, it's another parameter that we use to characterize machines. We call it slip, or explain certain profiles. We call it slip. Slip is basically this slip speed divided by the synchronous speed. Okay, so let's see how this is useful. Let's say our slip is 0. If slip is 0, that essentially means the motor is rotating at the synchronous speed, right? There is no relative motion between the rotor flux and the motor. Okay. However, if slip is 1, that means the motor is at a standstill and the synchronous speed is rotating at that synchronous frequency. Okay, so in between, you can see the motor transitioning from 0 speed to accelerating to the synchronous speed, maybe close to that, practical speaking. Okay, this is a definition that we're going to use in analyzing our machines. Okay, and another way to look at the motor speed based on the slip and the synchronous speed. This is just a reformulation of the slip frequency equation. Electrical frequency of the rotor. We talked about this, right? Electrical frequency of the rotor. What is it? That's basically the slip speed. We talked about this, the difference between the synchronous and the motor speed, which we can write as S times synchronous speed. Okay, it's different from this because this is motor speed and this is the rotor speed, the rotor electrical speed. Okay. Okay. So looking at the frequency FRE, we can convert it into this form. P is the number of poles over 120 times synchronous speed minus motor speed. Okay. let's make sure we got this right. Slip. Yeah. So slip is equal to 1 minus omega m over omega synchronous. Therefore, you can say omega m is equal to 1 minus s, yeah, omega sync, right? Yeah. And then this is just for the overall slip frequency of the rotor. Okay, so this we can say omega slip. All right. Okay. So that's it for this discussion on induction machines. Please let me know if you have questions. It's going to get very interesting, and we're going to go into a little bit more modeling and then using some of these parameters that we defined in analyzing our machines. Okay. Thank you.